Welcome to our deep dive, into the Apollo Guidance Computer, the AGC.
Ah, yes.
We both know the Apollo missions were monumental achievements, landing humans on the moon and returning them safely to Earth.
Absolutely.
And today we're going to delve into the computational marvel that guided those missions,
Right.
the AGC.
Fascinating piece of technology.
It's remarkable to think that a computer with less processing power than a modern-day smartwatch accomplished such a task.
Really puts things into perspective, doesn't it?
It does.
The AGC's computational power is indeed striking when compared to modern technology.
Yeah.
It operated with a mere 72 kilobytes of read-only memory and only 4 kilobytes of RAM.
Wow.
These severe limitations demanded ingenuity from the engineers and programmers who designed and built it.
It really is a testament to their skill that they were able to accomplish so much with so little.
It is.
Let's start by examining the AGC's unique memory systems.
Okay.
It employed two distinct forms of memory: core rope memory for its ROM and magnetic core memory for its RAM.
Two very different approaches.
Clearly.
Yeah.
The use of core rope memory for the AGC's ROM is particularly fascinating.
Yeah, how so?
Instead of relying on silicon chips like modern computers, the AGC's ROM used a system of wires meticulously woven around tiny magnetic cores.
Wow.
The presence or absence of a wire through a core represented a 1 or a 0, respectively.
Interesting.
Each wire held a specific bit of data crucial for the AGC's operation.
This method of weaving wires through cores, while incredibly space-efficient, was labor-intensive and prone to errors.
Absolutely.
Imagine a single misplaced wire could render the entire memory module useless, requiring the process to begin anew.
A lot of pressure on those folks.
Oh, yeah. This delicate task must have placed immense pressure on those responsible for creating these memory modules.
I can only imagine.
Despite this intricate and delicate process, core rope memory proved to be an effective solution for storing the AGC's critical programs and data.
Yes, it did.
But I understand the AGC's 15-bit architecture couldn't directly address the full 72 kilobytes of ROM.
To overcome this limitation, the engineers ingeniously divided the memory into 36 banks, each accessible one at a time.
A clever workaround.
Now let's move on to the AGC's RAM, which employed magnetic core memory. How did this differ from the core rope memory used for the ROM?
Well, both systems relied on magnetic cores to store information. Magnetic core memory utilized the direction of the magnetic field within the core to represent a 1 or a 0.
Okay.
This simplified the manufacturing process compared to the weaving required for core rope memory.
I see.
However, each bit of data in MCM required a dedicated core, making it both heavier and less storage efficient than the woven ROM.
And that must have had an impact on the software as well, right?
Absolutely. These constraints heavily influenced the software development, pushing programmers to optimize every line of code.
Given the need for efficiency in both hardware and software, it's clear that the AGC's architecture is a key component in understanding its success.
Right.
Could you elaborate on its design a little?
Certainly, the AGC utilized a 15-bit word structure with an additional parity bit for error detection.
Okay.
So each piece of data the computer worked with was 16 bits long. 16 bits carried the information, while the 16th acted as a check to ensure data integrity.
Okay.
This parity bit guaranteed that the total number of 1 bits in a word was always odd. If the count was even, it signaled a data corruption.
So this parity bit acted as a simple but effective way to detect errors.
Precisely.
And I understand it used registers to manipulate this data.
Yes, to manipulate this data, the AGC had 8 central registers,
Okay.
essentially the workhorses of the system.
Okay.
These registers were physically implemented using flip-flops, which were expensive to produce at the time. Therefore, only the most essential registers were built this way.
Could you give us some examples of these crucial registers and their functions?
Of course, one of the most important was the accumulator, or A register.
The A register.
It served as a general-purpose workhorse involved in most calculations.
So like the main one.
Think of it like the primary workspace where the AGC performed its arithmetic operations.
Gotcha.
Then there's the L register, the lower product register,
Okay.
which was used for double precision calculations,
Okay.
providing extra accuracy when needed.
Gotcha.
The Q register stored the return address of a function, a vital mechanism for program flow control.
Interesting. And there were more.
Yes. The EB and FB registers controlled the switching between the 36 memory banks for RAM and ROM, respectively.
between the banks?
The Z register functioned as the program counter keeping track of the next instruction to be executed.
Okay.
And the BB register was rather unique. It allowed for the simultaneous selection of both RAM and ROM banks,
Interesting.
a capability that facilitated data transfers and program execution.
Makes sense. And you mentioned an unnamed register. What was that for?
That's correct. There was one unnamed register hardwired to the value 0.
Hardwired.
Used primarily for resetting other registers to a known state.
So like an initialization thing.
While not technically a flip-flop register like the others, it was still considered a central one due to its role in initialization and control.
Makes sense.
In addition to these 8 central registers, the AGC also employed an additional 40 memory-mapped registers dedicated to specific tasks.
Wow.
Further expanding its computational capabilities.
So far, we've explored the AGC's memory systems and its architecture.
We have.
Now let's dive into the instruction set, the language that dictated the AGC's operations.
Okay.
This seems like a logical next step in our exploration.
Indeed, this is where we see a notable evolution from the initial Block I AGC, which had a limited set of 12 basic instructions, to the more advanced Block II, which boasted a set of 41 instructions.
Wow. So a big jump.
This expansion enabled the AGC to handle more complex computations and manage input and output operations more efficiently.
It's fascinating that they were able to expand the functionality while still working within such tight constraints.
It is.
And I understand they even developed an interpreter to handle instructions not directly supported by the hardware.
That's right. This interpreter essentially acted as a software layer that allowed the AGC to execute instructions that its hardware wasn't inherently designed to handle,
Clever.
further pushing the boundaries of what this seemingly simple machine could do.
To illustrate the ingenuity of the AGC's programming, let's examine a snippet of the engine ignition code.
Sounds good.
This code showcases how the AGC used flags, which are essentially digital switches and registers, to control critical spacecraft functions.
Right.
Analyzing this code snippet should give us a glimpse into the meticulous work of the programmers.
Absolutely. Examining this code reveals how each step in the engine ignition sequence was meticulously coded, ensuring the engine's safe and controlled activation.
I see.
It's a testament to the programmer's skill in manipulating limited resources to achieve such a complex and vital task.
It really is.
The complexity of controlling a spacecraft's engine with such limited computational resources highlights the intellectual prowess of the individuals who wrote the software for the AGC.
Let's shift our focus to the AGC's user interface, the DSKY.
Okay.
This was the astronaut's primary means of interacting with the computer.
Right, DSKY, which stands for Display and Keyboard, can be viewed as a precursor to modern computer interfaces.
Okay.
It featured indicator lights for various system statuses, 7-segment displays to show numerical data, and of course the keyboard for input.
That sounds very different from what we're used to today.
Unlike today's graphical interfaces with icons and windows, astronauts interacted with programs referred to as verbs and data referred to as nouns.
Interesting. So a verb-noun system.
Precisely, this system allowed the astronauts to initiate programs and manage data with a limited set of commands crucial in the demanding conditions of spaceflight.
So it sounds like this verb-noun system, while simple, was designed for efficiency and ease of use for the astronauts in a high-pressure environment.
Exactly.
And I understand there was a rudimentary operating system known as the executive behind all of this.
Yes, behind the scenes, a rudimentary operating system known as the executive managed all this input, scheduled programs, handled exceptions, and interacted with the spacecraft's various systems.
So the executive was essentially the brain behind the DSKY, coordinating all its activities and interactions.
That is an apt analogy. It ensured smooth operation and allowed the astronauts to focus on the mission's critical aspects without getting bogged down in the intricacies of computer management.
Another testament to the AGC's ingenious design.
Indeed, it's truly fascinating how they integrated all these elements to create a reliable and effective system for such a critical mission.
Indeed, the AGC's hardware memory systems, architecture instruction set, and user interface all demonstrate the remarkable ingenuity and skill of the individuals who created it.
Absolutely.
This foundation sets the stage for our next discussion exploring the AGC's reviews and legacy and understanding its impact not only on the Apollo missions, but on the field of computing as a whole.
I'm looking forward to it. The Apollo guidance computer's brilliance wasn't just in its innovative technology, but also in its lasting impact.
Right.
Let's explore what experts have to say about its legacy, beginning with John Loeffler's perspective. In his article, In Defense of the Apollo Program's Guidance Computer, Loeffler challenges the notion that today's calculators are more powerful than the AGC.
It's a common sentiment to compare the AGC's processing power to modern devices and find it lacking.
It is.
What's his reasoning for pushing back on that?
Loeffler emphasizes that while modern calculators might surpass the AGC in raw computational power,
Yeah,
they lack the historical context and the monumental task the AGC achieved.
I see.
Comparing the two is like comparing a modern car to a horse-drawn carriage solely on speed.
Right.
While the car is undoubtedly faster,
Yes.
it fails to acknowledge the technological leap the carriage represented in its time.
So Loeffler argues that focusing solely on processing power misses the bigger picture.
Exactly. Loeffler highlights that many of the AGC's software features were ahead of their time by decades.
Wow.
The technology itself was groundbreaking, pushing the limits of what was possible in the 1960s. To dismiss it as simply less powerful is to ignore the remarkable ingenuity and achievement it represents.
Now let's move on to Scott Manley's perspective.
Okay.
In his video, Rebooting a 50-Year-Old Computer, Making the Apollo Guidance Computer Work Again, Manley delves into the AGC's broader influence on the evolution of computing.
Right.
His focus is on the AGC's role in propelling silicon transistor technology forward.
Okay.
What does he have to say about that?
Manley's analysis highlights a fascinating aspect of the AGC's impact.
Yeah.
He points out that the development of the AGC coincided with the rise of silicon transistors and integrated circuits.
Interesting.
As the AGC transitioned from bulky discrete transistors to more compact integrated circuits, it generated a surge in demand for silicon technology.
So this surge in demand, as Manley argues, played a crucial role in the advancement of silicon-based computing.
Precisely. Manley argues that the AGC's reliance on silicon transistors, particularly integrated circuits, helped accelerate the development and miniaturization of these components. This, in turn, paved the way for the personal computers and smartphones we use today.
It really is a fascinating thought.
It's a compelling argument that demonstrates the ripple effect of technological innovation.
The AGC's impact on silicon technology is certainly a fascinating aspect of its legacy.
It is.
Now let's examine the Wall Street Journal's analysis of the Apollo 11 computer error, which occurred during the lunar descent.
Okay.
This event provides valuable insight into the AGC's software design.
Right. The Apollo 11 computer error is a well-known incident.
It is?
A moment of tension during a critical phase of the mission.
Yeah.
Many feared the worst when the AGC started flashing error codes during the lunar descent. However, the AGC continued to operate, executing essential guidance and maneuvering programs, allowing the lunar module to land safely.
Incredible.
Yeah.
The Wall Street Journal piece delves into the investigation that followed this incident.
Right.
What did they uncover about the cause of the error and the AGC's response to it?
The Wall Street Journal interviewed Don Iles, the programmer who wrote the descent code.
Okay.
The investigation revealed that the error stemmed from a miscommunication with a radar system. That flooded the AGC's memory with unnecessary data.
So an unexpected influx of data caused the error.
Yes, but what's truly remarkable is that the AGC was designed to handle such overloads.
Wow.
It had a built-in mechanism to reboot, purge its memory, and then seamlessly resume operations from where it left off.
So it basically just reset itself.
Essentially, yes.
That level of software resilience is impressive even by today's standards.
Indeed, it speaks volumes about the foresight and meticulous planning that went into the AGC's software development.
Yeah.
The engineers anticipated potential issues and designed the system to handle them gracefully.
It's a really remarkable piece of engineering.
This robustness, combined with the AGC's pioneering technology and its influence on the evolution of computing, solidify its legacy as a remarkable feat of engineering.
So we've covered a lot of ground in our exploration of the AGC, from its unique memory systems and architecture to its role in the Apollo missions and its broader impact on computing.
Yeah, it's been quite a journey.
The AGC's story is a testament to human ingenuity and our capacity to overcome technological challenges.
It really is.
It serves as an inspiration to engineers, programmers, and anyone striving to achieve ambitious goals.
Absolutely.
It's remarkable to consider what the AGC accomplished with technology that seems almost primitive compared to what we have today.
I know, it's amazing, isn't it?
This contrast underscores the power of human creativity and the importance of perseverance in the face of limitations.
Definitely.
The AGC's development was marked by numerous constraints, limited memory processing power, the weight restrictions of space travel.
Right, so many hurdles.
Yet the engineers and programmers rose to the challenge, creating a system that not only met the demands of the Apollo missions, but exceeded expectations in its reliability and functionality.
They really did an incredible job.
The AGC's legacy extends far beyond those leaner missions.
It does.
It represents the spirit of exploration, the relentless pursuit of pushing technological boundaries, and the transformative power of innovation.
It's a powerful symbol.
It serves as a reminder that groundbreaking advancements often emerge from necessity, driven by a desire to overcome seemingly insurmountable obstacles.
That's a great point.
As we conclude our deep dive, I'm left with a thought-provoking question for you, our listeners.
I'm all ears.
How would the trajectory of computing have unfolded differently if the AGC had not pushed the boundaries of technology in its time?
That's a fascinating question.
Would we have personal computers, smartphones, and the interconnected digital world we know today?
It's hard to say for sure.
It is.
But the AGC's development and deployment spurred innovation in silicon transistor technology, software design, human-computer interaction.
So many areas.
It's difficult to say for certain what the world would look like without the AGC's contributions.
Right.
However, it's safe to assume that the landscape of computing would be vastly different.
I think that's a fair assessment.
The AGC's legacy continues to inspire. It reminds us that even seemingly small steps forward can have a profound impact on the course of history, shaping the world we live in and paving the way for future innovation.
So the next time you interact with a computer, take a moment to reflect on the legacy of the Apollo guidance computer.
A good reminder.
A machine that defied limitations and helped humanity reach for the stars.
The AGC stands as a testament to the power of human ingenuity and a source of inspiration for generations to come.
Well said. And that concludes our deep dive into the Apollo guidance computer. Thanks for joining us.